This is my attempt to create a crash course on star life cycles where I talk really fast and you can't quite comprehend what I'm saying. Let's start with where we are now. We are in a galaxy called the Milky Way where Earth and other planets awkwardly rotate what we call the Sun. Now, I will explain how Earth got into its awkward rotation around the Sun by appearing to go off topic because I'm going to tell you about stars. Now, in this picture, we see a giant dust cloud in the center, which we call the stellar nursery, and there's an arrow pointing towards the protostar, then towards the main sequence, and it kind of just splits off into two. To the left, we got the red giant, which turns into the planetary nebula, and turns into white dwarf and a black dwarf with an arrow also to the stellar nursery. But then on this side, we got a really big planet that we call a supergiant, and an explosion happening, and an arrow to the stellar nursery again, and a neutron star, and a black hole. It's kind of a lot going on there. Where are we in these phases? We are in the phase of the main sequence star. The energy you feel from the sun today is created by the fusion of hydrogen atoms to create helium atoms. Fun fact, 90% of the stars are main sequence stars. If you didn't know, this is the comparison in size of Earth to the sun. When the core of our sun runs out of hydrogen atoms, it will become a red giant. Gravity is now stronger than the pressure of the fusion and starts compressing the sun. Helium will now combine to make carbon, and this actually expands the sun. Believe it or not, but when the sun expands, there is a chance Earth will be swallowed in the process. Since the sun will have more area to cover, the heat will decrease to about half of its original temperature. Once the fusing is over, gravity will take over again. This time, the sun will collapse and eject its shell of gas, creating what is called a planetary nebula. Slowly, the gases just spread out and make their way through space. The white dwarf is just the rock of the sun, except without its gaseous cell, although still hot and emitting light. Now, the black dwarf is actually just a rock. There's more heat and, well, there's no heat or light coming from it at all. That was what our sun's going through. But what if our sun was a little bit bigger? This time we get a supergiant, which is essentially the same thing as a red giant, but just bigger. To get a supergiant, the main sequence star needs to be 5 times more massive than that of our own. The only difference is the supergiant can make way cooler elements and it'll live longer. A supernova. Oh, it's just a really big explosion. They'll destroy anything in its path. Let's get real now. Think of all the energy a sun creates in its lifetime. Now think of all that energy being released in a second due to an explosion of a massive sun. The force from the explosion is what creates the rest of the elements on the periodic table. Now, depending on the mass of the sun before the supernova, it can lead to two options, a neutron star or a black hole. We will start with the neutron star because it just sounds way more interesting than black hole. This occurs if the mass of the star is roughly 8 to 20 times greater than that of our own sun. The leftover star is about a city size, yet it has a mass greater than our sun. But that's scary. Since this star is so dense, it literally squeezes protons and electrons together to create neutrons, hence the name. Now let's talk about what happened to my slide. Whatever you mean, you probably already know about black holes anyways. Oh, wow, there's my slide. Looks like you get to listen to me talk even more. A black hole comes from a supernova of a star whose mass is 25 times greater than our own sun. The implosion is so great that it just never stops sucking mass to a single point. The stellar nursery is pretty much the typical thought of space where there's nothing and you just float around, but there's definitely something going on. It's a huge molecular dust cloud that's just collapsing on itself. These molecular clouds came from the planetary nebula when the red giants disposed of their gaseous shells. The protostar is the real deal. This is where planets are formed. When the powerful wave of the supernova hits the stellar nursery, a rotational movement is created, keeping the more dense elements towards the center and sending the lighter elements towards the outside. Atoms collide, forming chunks in which collide with other chunks to continuously get bigger and bigger. The biggest chunk will become the star. Since denser elements stay towards the center of the rotation, you can understand why the planets closer to the sun are more dense compared to the gaseous far-away planets. And that's the way the cookie crumbles.